Hello everyone. In this lecture I shall discuss the applications of double integral. Now recalling the previous lectures, the double integral of a function fxy over the given region R is double integral R fxy dy dx. Now if we want to change the order of the integral, we write dx dy, then accordingly the limit will be changed as I have discussed in the previous lecture. Right, so this is by changing the order of the integral. This representation or this representation, both will give the same answer. Moreover, in some complicated situation, we may also change the variable. Right? If we put x is equal to r cos theta, y is equal to r sin theta, accordingly Jacobian is x r x theta, y r y theta, the partial derivatives determinant, and it is your r. Okay? And this integral will be f of r theta. Now this xy is replaced by r theta, and some extra thing, this Jacobian j is multiplied and dr d theta. This representation also give you the same answer. Okay, so this is basically to make the complicated situations easier. Now before coming to the applications of the double integral, let me to introduce myself. Myself Professor Susanta Kumar Paikray, currently working as a professor of mathematics at Veer Surendra University of Technology, B.Sc, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the applications of double integral. Coming to one, the area of a region, the area A of a region R in xy plane is given by your area A is equal to double integral over the region just dy dx, right? And next, coming to the volume beneath the surface and above the region. Coming to second application, the volume V beneath the surface z is equal to f of xy, and above a region R in xy plane is V is equal to double integral z into dy dx, right? Or otherwise we can interpret it, the volume V in xyz space here. Okay, this is the triple integral dx dy dz, right? So in xyz space, 3D space, right? In xyz coordinate system in 3D space. Okay, now coming to the third applications, let fxy be the density. Here the density means the mass per unit area, because you are talking about two dimension. Mass per unit area is given, right? In a distribution of mass over a region R in xy plane, then the total mass M is double integral over the region R, the density is fxy, and the area factor here is dy dx. Okay, if here fxy is 1, you note that if fxy is 1, uniformly distributed, fxy is 1 here, right? Then your mass is equal to the area of the region, area of R, is not it? So now this density is mass is uniformly distributed over the region R, then it becomes your area. And coming to the fourth application, the center of gravity, let you denote it x bar y bar, in the distribution of mass in the distribution of mass over a region R is given by, so in the same region we know the total mass, then your what is your x bar? Your x bar is in continuation to this, okay, in continuation to this 3, x bar is equal to 1 by m double integral x into fxy dy dx or tx dy, that depends upon the order, and y bar is 1 by m and double integral over the region. For y bar, y is multiplied, y fxy is your density dy dx. Okay, next coming to the moment of inertia. Next coming to the fifth application, the moment of inertia of the mass in a region R. Now it is about x-axis, it is Ix is equal to double integral over the region R, it is y square, the density is fxy, it is dy dx, and here about y-axis it is denoted by y is double integral over the region R, here x square into fxy dy dx, and the moment of inertia about origin, or what we call it the polar moment of inertia, it is denoted by I0, so this is Ix plus Iy, or it is, if you add these two, it is double integral, it is x square plus y square, it is added x square plus y square. Now the density is fxy dy dx. So these are the applications. Let us solve some problems. Consider an example. Let fxy be the density of the mass in the region. The region is this 0 less than y less than 1 minus x square root over. So if you look into the region here, coming to the solution, right, here y is equal to 1 minus x square. What does it mean? Root over. So implies y square is equal to 1 minus x square. This means x square plus y square is equal to 1. So this is a circle with center 0, right? This is a circle with center at origin and radius is equal to your 1. Okay. Now this y coordinate 0 less than x less than 1 means it is in the first quadrant. 0 less than x less than 1. What does it mean? It means in first quadrant only. First. So we should have a idea of this region, the geometrical representation of the region. So the region here is this, right? So this is a circle and the region here is this only. Okay, so it is only this in the first quadrant it is given. So this is the region you are given, right? So this is the region R given here. So this is the region R, right? This is the region R. So here this is y is equal to 1 minus x square root over, right? If you are taking the vertical strip here and this is your y equal to 0 and this is your 0 0, this is your 1 0. So this x-axis, in x-axis horizontal it slides from 0 to 1, this point to this point it slides. Okay, so this is the geometry of this region. Now coming to the total mass. Okay, coming to the total mass. Here m is equal to double integral fxy dy dx over this region R. Okay, so this is equal to integral 0 to 1 minus x square root over, and 0 to 1 it is 1 into dy dx. So this is nothing but the area of this region. You may integrate it or I may write it. It is 1 by 4th the area of the circle. So this is 1 by 4 pi into 1 square. So this is pi by 4. So here the total mass here is the pi by 4. Right, now coming to the center of gravity. center of gravity. Your center of gravity is here C x bar y bar. Now what is x bar? X bar is 1 by m double integral x f xy dy dx. Now if you change into the coordinate system, if we change this, we write it 1 by m double integral in polar coordinate system. X is here r cos theta into f r theta, and this Jacobian j is extra multiplied, it is dr d theta. Then it becomes here easy. It is difficult, I mean to say it is lengthy, and this approach is easier approach now. Okay, how we get it? We put x is equal to r cos theta and y is equal to r sin theta. So Jacobian is my r, right? Now if you really want to evaluate the integral in view of this, then it will be my 1 by pi by 4, means 4 by pi. The limit is 0 to 1, and 0 to 1 minus x square root over, it is x into 1 into dy dx. Okay, we have to evaluate it. Or alternatively, which is same thing as we evaluate it, then this integral is quite easy. It is my 4 by pi, this is r cos theta double integral r cos theta and dr. I am writing r, the radius is 1 here, right? And theta in the first quadrant, the angle of rotation here is 0 to pi by 4 only, pi by 2 only, sorry, this is pi by 2, 90 degree, pi by 2. So it is 0 to pi by 2. Okay, it is cos theta. And what is your Jacobian? This Jacobian is your r, and it is dr d theta. Okay, so this is equal to 4 by pi, 0 to pi by 2, and here 0 to 1, here r square cos theta, d r d theta. It is multiplied together, right? So we can separate them also instead of the sequential evaluation. 0 to pi by 2, this is for your theta, so I can separate it cos theta d theta, and I can separate it for r, 0 to 1 r square dr. Okay, so it can be separated. In first lecture I have told you, if the variables are clearly separated, there is no intermix, no implicit, then also we will able to write as the product. So this is 4 by pi, the integration cos theta is sin theta, it is here 0 to pi by 2, then it is here r cube by 3, and here 0 to 1. So if you evaluate this integral, this will here 4 by pi, sin pi by 2 is 1, sin 0 is 0, into it is 1 by 3 minus 0. Okay, so this will be here 4 by pi into 1 by 3, so it is 12 by pi. So it is your answer for the your moment of inertia, center of gravity x bar. Okay, x bar. Then coming to y bar, sorry, it is 4 by 3 pi na, it is here 4 by 3 pi. Accordingly your y bar will be 1 by m double integral your y fxy dy dx, and if you change the variable 1 by m double integral, it is y is r sin theta, and it becomes here f r theta, and Jacobian extra multiplied, it is dr d theta, right? So this is pi by 4 means 4 by pi, here 0 to r limit of theta, 0 to pi by 2 in the first quadrant, and 0 to r limit is 0 to 1 radius, it is r sin theta, and this is your 1, and here Jacobian is your r dr d theta. Okay, since we can write it explicitly separating r and theta, so we can write 4 by pi, here 0 to pi by 2, this is for your theta, sin theta d theta, and separating r, it is your r square sin theta d theta. And similarly if you evaluate it, it is here again 4 by 3 pi, Okay, now coming to the moment of inertia. Now coming to the moment of inertia, here about x-axis, Ix is equal to double integral over the region R, it is y square fxy dy dx. Okay, so this is equal to 0 to 1, 0 to 1 minus x square root over, it is y square into 1 and it is dy dx. You may evaluate it directly, or if we change the variable here, or you may write it 0 to pi by 2 for my theta, right, and 0 to 1 for my r. Inner is r, so it is dr, and then d theta, and y is r square sine square theta, f is your 1, Jacobian is your r. Okay, then it is, the evaluation is quite easy. We put x is equal to r cos theta, y is equal to r sin theta, and Jacobian is your x r x theta, y r y theta determinant is equal to your r. So we change it to the polar system. Okay, so now this integral is quite easy. 0 to pi by 2, it is for your theta is your sine square theta d theta, and your rq 0 to 1 rq dr. Okay, so now if we evaluate the integral, it is here 0 to pi by 2 1 minus cos 2 theta by 2 d theta, it is here r 4 by 4 0 to here 1. Okay, so this will be, if you integrate it, it is half theta 0 to pi by 2 minus 1 by 4, integration of cos 2 theta is sin 2 theta divided by 2, sin 2 theta, it is 0 to pi by 2, then into this into here 1 by 4 minus 0. So this is equal to, this is pi by 2 sin pi sin 0, this becomes here 0. So this is equal to pi by 4 into 1 by 4. So this is pi by 16. Okay, similarly we find moment of inertia about y-axis. Iy is equal to double integral over the region R. It is x square, for y it is x square, for x it is y square, it is fxy dy dx. If you change the variable, right, x is equal to r cos theta, y is equal to r sin theta, so that means my Jacobian is equal to r. So this integral will be reduced as to x is r cos theta into f is here 1 f r theta into Jacobian here dr d theta, right, dr d theta. So we can write it here 0 to 1 is radius, 0 to pi by 2 it is in the first quadrant, here r cos theta, f is here 1, Jacobian is r, in inner limit is theta, then here r. Okay, so similarly if we evaluate it, it is your x square r square cos square theta. Okay, and if you evaluate the limit, we will get it again the same way, or if you evaluate it, it is 0 to 1, it is r square cos square theta, it is here for your r it is rq dr, and 0 to pi by 2 it is cos square theta d theta. If you evaluate this integral, it is r 4 by 4 0 to 1, and it is 1 minus cos 2 theta by 2 integration 0 to pi by 2 d theta. Okay, so this is plus. So similarly it will give you 1 by 4 into, it is 1 by 2 theta 0 to pi by 2 plus integration of cos is sin 2 theta by 2 0 to pi by 2. Now this will give you 0 because sin pi 0 sin 0 0, so this will be 1 by 4 into 1 by 2 into pi by 2. So this is here pi by 16. Okay, now what about I0? So therefore I0 is Ix plus Iy, so this is equal to 2 pi by 16 is your pi by 8. Okay, so this is the answer. So coming to one more example, find the volume beneath the surface. This is the surface, and above this square with vertices this. So here as you see, this square here is, the square here is, this is minus 1, 1, minus 1, minus 1 in the third quadrant. Fourth quadrant it is 1, minus 1, it is here 1, 1, and it is here minus 1, 1. Okay, so now the formula for the volume is here double integral over the region R. It is z into fxy, z into dy dx, z dy dx. Okay, so what is the limit of y? It is straightforward. The limit of x 0 minus 1 less than x less than 1, and the limit of y is also straightforward, minus 1 less than y less than 1. So this integral becomes here minus 1 to 1, minus 1 to 1, z is x square plus y square dy dx. Okay, and if you evaluate the integral, it is minus 1 to 1. If you evaluate this inner integral here you treat x is equal to constant here, so x square it is y, and plus y cube by 2, y cube by 3, right? The limit is minus 1 to 1 dx. So in place of y we are substituting this, so this is equal to integral minus 1 to 1, x square remains silent, it is 1, minus of minus 1 2, plus 1 by 3 remains silent, it is 2y 2 into, it is 2, it is 2 here, so this is dx. So this is equal to minus 1 to 1, 2x square plus 2 by 3 integral dx, or this function being even we can write it twice integral 0 to 1, 2x square plus 2 by 3 dx. If you evaluate this integral, it is 2, it is 2 by 3 x cube plus 2 by 3 x, limit is from 0 to 1, so it is 2, it is 2 by 3 into 1 minus 0 plus 2 by 3 into 1 minus 0, so this is equal to 2 into twice 2 by 3, twice 2 by 3, it is your 8 by 3. So this is your answer. Okay, this is your answer. So to conclude, once you are smart in evaluating the double integral, then the applications, just you remember the formula and simply evaluate the integral. Find the volume beneath the surface and above the region. Find the volume beneath the surface and above the region. Find the total mass. Find the area. Find the center of gravity. Find the moment of inertia. Just remember the formula and apply the double integral. So first you have to understand the how to evaluate the double integral. So for which we should refer my previous 2 lectures. Okay. So in the subsequent lecture, in the upcoming lecture, I will discuss one of the most important aspect, that is the Green's theorem. Okay, Green's theorem. So video is getting lengthy, we should close here. Now if you feel this lecture is helpful and interesting, please like and subscribe to this channel, so which will boost my motivation to upload subsequent lecture for your benefits. So the subscription will give the benefit of you will get the lecture in the screen when it is in your screen when it is uploaded, right? So with this we should close the lecture here. Thank you all.